So in this video I want to look at another application of derivatives, and this is just a kind of another step beyond our first derivative test. It's commonly called a second derivative test, or checking the concavity of a graph. So to kind of introduce you to the idea, if you're not familiar already with the idea of concavity, that's really the direction the graph is opening towards. So I have here y equals 1/4 x to the fourth minus 2x squared. When we look at the concavity, we're looking at, say, on the left part of this graph, you see how it comes down, it increases back up, and the graph is kind of facing upwards, or it's opening upwards. That means it's concave up. And then in the middle part of the graph, you see around the origin, it's kind of opening down. You see it increasing and changing to decreasing. That's concave downwards, and then to the right of that, as it begins back up, you have another time it's concave up. Concavity doesn't depend upon the nature of the intervals, if it's increasing or decreasing on an interval, but it's related to it because concavity is the rate of change of the rate of change, or it's the rate of change of the slope of the tangent line. So if something is concave upwards, what that is really telling us is that the tangent line slope is increasing. So if we think about what that means, say for example on this graph it's concave up, the tangent line slope on the left edge of this graph as we look at it is pretty steeply downwards. It's decreasing, but it's getting less steep and less steep, so really it's getting positive. So the tangent line slope itself is increasing, getting more positive. It reaches a point where there's a relative minimum there. It changes direction, the graph increases again, and it reaches a point where the tangent line continues to get steeper and the slope is increasing, but then it changes and it begins to lessen. The tangent line slope gets smaller until it reaches another extrema. The points that it changes at we call points of inflection. So I wrote here concave up is tangent line slope increasing. I'll write here below it concave down means that the tangent line slope is decreasing. So how do we find these, and how do we find the points of inflection as I had mentioned? Well, if we think about it, the first derivative is the slope of the tangent line. So if we want to look at how that's changing, what's a rate of change? A derivative. What's the derivative of the derivative? Well, we call it the second derivative. So if we want to find the point of inflection, we want to set the second derivative equal to 0 and solve for x. And that's pretty much telling us the point at which the tangent line begins to change from increasing to decreasing, or vice versa. And if we want to tell whether a graph is concave up or concave down, just like with our first derivative test, we say, is it greater than 0? Concave up. Is it less than 0? Concave down. So this may seem a little bit harder to kind of see graphically, but I think as we work an example and as you work with this more, it gets a lot easier. So let's go ahead and work this problem. If I have y equals 1/4 x to the fourth minus 2x squared. Now I want to know, what is the concavity, what are the points of inflection? Well, first I need to take the first and second derivative. So the first derivative, y prime, will simply be x to the third minus 4x, just using our power rule and our sum and difference rule. And our second derivative is another easy one. We get 3x squared minus 4. So now I have the second derivative. How do I gauge the concavity? Well, first I need to find the points of inflection. So I'll set that equal to 0. 3x squared minus 4 equals 0, and solve for x. So to solve, we'll add 4, we'll get 3x squared equal to 4, divide by 3, we get x squared equals 4 over 3, which when we take the square root, we get x equals plus or minus the square root of 4 over 3, which simplifies to plus or minus 2 over the square root of 3, and if you want to rationalize the denominator, plus or minus 2 square roots of 3 over 3. So these are the points of inflection, and I'll write that there. Points of inflection are x equals 2 square roots of 3 over 3 and negative 2 square roots of 3 over 3. Let's look back at our graph and see what is that telling us. Those are the points around here where the graph seemingly changes from opening up to opening down, because as you come down the graph here, it's opening upwards there. But if you notice, around that point it turns and it's opening downwards, and then it turns again and it's opening upwards. So the points of inflection are where our concavity is changing, and that's where the rate of change of the slope is changing, because on our first leftmost part of the graph here, the slope is increasing. Although the function's decreasing, it's beginning to decrease less and less, then it begins to increase, so the slope is continually increasing. At that point of inflection, the slope ceases to increase and begins to decrease again. And at the instantaneous point, the point of inflection is where that change occurs. So once we have those points of inflection, we can find the concavity, because just like with our first derivative test, we'll set up intervals to test the concavity. So I'll say from negative infinity to negative 2 square roots of 3 over 3, from negative 2 square roots of 3 over 3 to positive 2 square roots of 3 over 3, and from positive 2 square roots of 3 over 3 to positive infinity. These are our intervals, and I'm going to test points within it on our second derivative, and that's telling me what the concavity is on that interval. And just like we had said with the first derivative test, we're pretty much saying this is where it changes, so if we test any point within it, every other point has to be the same. So I want to know what is y double prime of some number on that interval. We'll say negative 5. For the middle one, what is y double prime of 0? And for the final one, what is y double prime of positive 5? And whether these values are positive or negative tell us whether it's concave up or concave down. When you calculate that, you get a positive for the first interval, negative for the second, positive for the third. And that's just plugging those numbers into the second derivative. So that tells us that on the interval from negative infinity to negative 2 square roots of 3 over 3, and from 2 square roots of 3 over 3 to positive infinity, the graph is concave up, because the second derivative is positive. And from negative 2 square roots of 3 over 3 to positive 2 square roots of 3 over 3, where our second derivative was negative, that tells us it's concave down. So if we kind of relate that back to the graph, that's telling us, as I had mentioned earlier, those points at the end of the intervals, negative 2 square roots of 3 over 3, positive 2 square roots of 3 over 3, are our points where it's changing at, and we see the graph opening upwards on that leftmost interval, downwards in the middle interval, then upwards in the rightmost interval. And we can do this with practically any graph. If we can take the derivative, solve for, or take the second derivative and solve for x, we can find the points at which the tangent line ceases to continue increasing or decreasing. We're finding really how to optimize, or how to find the point where your tangent line is increasing or decreasing the most.